Alright, hello and welcome to another video lecture. Today we're going to be talking about accretion and orbital motion. And you're probably realizing that at this point most of these are going to be around 20 minutes long. I'll try to keep them short when I can, but today probably will be a little bit longer as well. And it's just because I'm realizing that I need more time to explain these things. But anyway, let's get started and I can try to move through this as quickly as possible for you. Okay, so last time in our lecture we talked about how gravity is the driving force of what creates planets, and we went over how the Big Bang formed the universe and how that kind of breaks down. But we didn't talk about the specific process by which planets are formed, and it's actually a pretty simple process. It makes sense. It's called accretion. And so accretion is the accumulation, so you want to write this down, accretion is the accumulation of particles into a massive object by gravitationally attracting more matter. So most astronomical objects such as galaxies, stars, and planets are formed by this process from that solar nebula. So you can kind of see this picture down here so the universe started out with very small particles. If you remember, we talked about helium and that's hydrogen and that's helium. And then they started to collide into each other and stick. And when they did this, they collided and stuck. They got bigger and bigger, and as they got bigger and bigger, they got more gravity. And as they got more gravity, that allowed them to have more particles start to get pulled into them. And so that's kind of how the planets formed, right? From this dusty, gassy material that was the solar nebula thing. As it was spinning, there was a lot of collisions going on, and these particles started colliding into each other. And this reminds me of something and that is something I learned about called the Pareto principle. And this is actually an economics terminology, and I just want you to remember it, so definitely write it down. The Pareto principle is how we describe in economics the fact that the wealth of an economy lies in a small percentage of people. So a small percentage of people, say 80% of events in an economy come from the 20% of the causes. What that means is a small percentage of people or businesses are the ones doing 80% of the business. So why am I talking about this Pareto principle? Because I think it's another good way of describing accretion. So if we look at some of these examples, the sun holds 99.8% of the mass in the entire solar system, and the nucleus of an atom holds 99.9%, the mass of the entire atom. It's like the Pareto. It's like the universe uses the Pareto principle. Pareto is just an economic scientist, but I just think it's interesting how that we see this happening all around us. Wealth, power, matter. With matter, it's the law of gravity, but you can see how this kind of tends to happen, the accumulation of something in one spot. So that's why the sun holds most of the matter for our solar system. It just got so big that it started sucking everything in, and there was very few particles, 0.2%, that were able to escape. And that's what made and collide into their own planets, like the gas giants and the rocky planets. So that's kind of crazy. And this is a good representation of how this accretion happens, but really also how what I like to call the Pareto principle. There's other names for it, but this is what I've heard it described as. How did the sun get this big? So why is it that the sun gets this big, and why do other solar systems tend to form like this? So how did it get this big, and why? Well, we know it got this big by accretion, but why is it so much bigger than everything else? And I love this picture, even though it's a little bit fuzzy, because it's such a good relative size of just how giant everything is compared to each other. So Jupiter, which is 1,000 times the size of the Earth, is just so dwarfed by our sun. And so this sun, because it's so massive, has so much gravity, and so it just continues to pull everything into it, and somehow the rest of the planets are managing to escape this. So that brings me to my next point. So my next point or question for the day is, how did the rest of these bodies kind of escape the massive gravitational force of the sun? And in other solar systems, how do other solar systems planets escape this? Well, to understand this, we got to go over the law of inertia. So you guys do need to know the law of inertia. So an object at rest remains at rest. You've probably heard this before. Or if in motion, it continues to move unless acted on by another external force. So however you want to write that down in the shortest way you can. You don't have to write all this out, but make sure you summarize this in your notes. So it'll continue to move in a straight line with a constant speed. So how do we describe the motion of planets around the sun or satellites flying around the Earth? So why is it that everything isn't just collapsing into this giant gravitational pull? Well, it turns out it's because of the law of inertia. All of this matter and mass in the solar system, or you could say, the satellites orbiting Earth, they have their own velocity. So let's kind of draw a picture here to describe this. So if we have Earth, okay, and we shoot a projectile into Earth, okay, if we shoot it with a low velocity, it'll go kind of like that, up and down. And if we give it more velocity, it'll go even higher, but it'll eventually fall to Earth. And even higher, it'll fall to Earth. And even more, and it goes to the edge. But what happens if we give it so much, we launch it at such an angle with so much velocity that it's able to leave the planet, right? But the gravitational force of Earth is going to be so big that it pulls it back down. But if we get the velocity just right, it's going to keep on missing Earth as it falls back down. So when we say something is in orbit, it's because it has this inertia. The inertia is it's going to keep moving. The force that's acting upon it is going to be gravity, but if it has enough velocity to overcome the distance of Earth, then it will just keep circling around Earth, and then it's in orbit. Well, it turns out this is what happens with everything in our solar system that's orbiting the sun and anything that orbits around our planet. So anything that's orbiting a larger massive object. It's actually, we like to think of them as just floating around the sun, but actually, or the Earth, when something is in orbit. But in fact, we'll talk about this a little bit more in a second, everything that's orbiting is in a constant state of free fall. So it's just that it's falling and it just keeps missing what's pulling it in. So inertia, so basically what I'm trying to say is inertia, that the law of inertia, that everything will kind of move in a straight line unless acted on upon another force, mixed with gravity. So this is what I want you to know. Inertia with gravity is what forms orbital motion. In other words, when something is spinning around. So that's where we're going to go next, is what is orbital motion? Because this is really important. Planets formed by orbiting the sun and accreting their own mass. So without these orbitals, everything would have just fallen into the sun. Okay? So the consequences of gravity and inertia are orbits. So the force of gravity is that force that keeps objects in orbit. Without gravity, without gravity, the moon and every other object would just keep moving in a straight line. One thing we should mention is the reason this happens is because space is what we call a vacuum. Okay, and a vacuum just means there's no particles. So there's no friction to slow anything down. So when we throw something on Earth, it eventually slows down, or when we're driving a car, it slows down because of friction, or because of any other kind of force, which you'll learn more about in physics. But in space, if something's moving, it'll just continue moving if something is moving in a straight line or has a velocity. So, because of Newton's first law, that law of inertia, so the law of inertia is Newton's first law, things would just keep moving away from Earth if we shot them out without gravity. So again, you have to understand, it's the mix of gravity. So these objects would continue moving in this straight line, but there's a constant force down. So instead of moving in that straight line, it moves in a pattern around Earth, and this is what we call an orbital. So everything moving around Earth, even the moon, is constantly being pulled back to Earth, but it just keeps missing. It's in free fall. It's in a constant state of free fall. around the Earth. And I don't know if you guys have ever seen those videos of people that have simulated in airplanes, basically no gravity, where they're floating in those airplanes, and a lot of people end up throwing up. That's because the airplane is just at in a state of free fall, and so that's what simulates them having no gravity. So that's a really interesting aspect of this concept of orbital. So in order to talk about orbitals, we do need to go through some of Kepler's laws. So there's 3 laws, okay, and these are the basics of them, and we'll kind of dive a little bit into each one, so you don't need to write them all down right now, but there's 3 laws, and that's what we're going to go over next. So Newton explained why things are happening when so these scientists started out by observing the stars, both of them, and the world around them. And so Kepler understood that when he looked at the stars, that these planets and everything in the sky seemed to orbit around the sun, the planets in our solar system, and then even that we were moving in our own solar system around a galaxy. And he understood this, and he understood orbital motion, and then Newton was able to explain why with inertia and gravity. So you guys now know what both of these are, and we're going to dive a little bit more into Kepler's laws, the what. So the first law of orbital motion, this is where I would write it down. So planets orbit on ellipses. So that's a really key point. So let's make sure you guys understand that. It does not happen where planets orbit in circles, perfect circles. Okay? So if you look down here, the white line is a perfect circle. Okay? And then you can see these other orbitals in blue and in red are ellipses. They're not perfect circles. They're basically squashed circles. And how we determine how a squashed something is with this word called eccentricity. So the higher the E value, so if E is greater than 0, then you're dealing with an ellipse. And the greater that number is, the more eccentric. So you're also dealing with something that is an eccentric circle. So you may have heard that word eccentric, somebody being eccentric. They're 2 different meanings, but you could probably make some correlation if you really wanted. But anyway, so the larger the E value, this is something you need to know, the more eccentric and the more elliptical, or the more squashed the orbital is. And so everything in our solar system, and as far as we can tell, every other solar system out there in our galaxy, orbits the sun in an elliptical path, meaning a squashed circle. So that's his first law of motion, this is how orbitals form. They don't form perfect circles. So you need to know that there are 2 types of orbitals. There's closed curves and there's open curves. And so in our solar system, all of the planets follow closed curves, meaning they all follow elliptical patterns around the sun. There are some things in our solar system that will form open curves, like things way out there, like comets and asteroids, and they'll kind of form these parabolic. You don't need to worry too much about that. But just know, the faster something is moving will dictate its orbit. And this makes sense, because if it's moving faster, it's going to escape that gravitational pull and just keep going. So there has to be kind of that sweet spot where it has enough velocity so that it keeps missing the gravitational pull, so it doesn't continue to crash back into it. Okay? So we mentioned this part about escape speed, so you guys do need to know what this is. It's the minimum speed needed to escape the force. So I would write this down. It's the minimum speed needed to escape the force of gravity of the central body pulling the object into a closed orbit. So again, if you're going to have something in orbit, it needs to have an escape. It has to have a speed greater than the escape speed. Or sorry, it has to have the minimum speed needed to escape the gravitational pull. So that force will have to, the force has to be greater than what will continue to pull it back down to the surface of the body. So like our moon, a better example is when we shoot astronauts into Earth orbit. They have to reach that minimum speed to get into orbit. so that they'll keep missing the Earth as they fall back down. So that concept is really important. And keep in mind, in physics, we go over all the in physics, when you take a physics class, you'll go over all the math involved in this, so you can figure out what type of speed will form what type of ellipse. But in this class, we don't do that. So it's more important that you understand the concepts. So that's what I'll be testing you on. So make sure you guys understand it. So if v is greater than the escape speed, if the velocity is greater than the escape speed, then it does not orbit. So all that means is if we shoot something off, let's say this is planet Earth, and its velocity is not greater than the escape speed, then it'll fall back to the surface. So we need the escape speed to be fast enough so that it shoots off, and as it pulls back towards Earth, it misses Earth, and then you are in orbit. Okay, so again, that's the concept you need to remember. The second law of orbital motion, basically what you need to understand is that there is anything that forms an orbital motion, there is what we call the focus point, and within any ellipse, and so remember an ellipse is the motion that the orbiting object follows. So if this is the sun, right, and this is a planet, then the focus will be somewhere off center. And that's important. So our planets in our solar system revolve around the sun in an ellipse, and it's non-central. So there's going to be times where the planets are closer to the sun and farther away from the sun. Okay? And this is true of anything that orbits. So even our moon, there's times when the moon is closer to Earth, and you guys have heard of this, when the moon is, we have certain patterns of when the moon just seems really giant in the sky. And it's closer to Earth, and this can affect the tides and stuff. That's because of its elliptical path. But the second law states, and this really comes from a mathematical equation that you guys don't need to know, but you do need to know the concept. So when the object is faster to the orbiting object, or the focus, then it moves faster. And this makes sense because that gravitational force that's pulling it in is going to be stronger. Okay, and so it's going to move faster when it's closer, and then as it moves farther away, that gravitational force that's pulling it in is going to be slower. But the point is that in the given time frame, they still sweep the same area. So this area here, and maybe I'll use a different color so you can see, this area in blue here takes up the same amount of area as this area in blue over here. So there's still that same amount of space, and that's because over here, when it's moving slower, it covers less ground, but it's farther away, so that's more space to cover, right? Whereas here, it's moving much faster, so it's going a farther distance in the same given time. So this is the same time frame, right? So same time here and here. That's the same time. But it's closer to the sun, so it's still the same area. So that's the second law of orbital motion, is that the sweeping area that's covered in an orbital motion is always going to be the same no matter where you are. So no matter if it moves faster or slower. So you need to understand all these concepts of the second law of orbital motion. Lastly is the third law of orbital motion, and this one I could give you a bunch of mathematical equations, and if you ever take physics you'll see them. But let's just simplify it, and it's pretty obvious when it comes down to it. It's not as obvious looking at the math, because the math, they actually have to prove that this is the case. We just take the math, and I'm just going to tell you what the math tells us. And it should be kind of obvious. The time it takes a planet to complete its orbit depends on the size of the orbit. And this is true of not just planets, but anything orbiting anything. So we know that Earth takes a year. What we say is 365 days, right? So I gotta pull this up so I can see it. So you can see that's where we are in years. So that's where a year came from, right? A year is how long it took takes Earth to orbit the sun. Pluto takes closer to almost 800 years to take one full elliptical pathway around the sun. So all that the third law of orbital motion states is that the farther you go away from the center object, the object you're orbiting, the longer it takes to complete that orbital. So the larger the ellipse will be, right? the larger that squashed circle will be. So you got to know Newton's 3 laws, understand the concepts behind them, and understand accretion and how I kind of put Pareto's law in there. We'll just kind of conclude everything. So the most important takeaway points from today: accretion, it's the process in which is thought to have created planetary bodies, the sun, planets, and asteroids, and this happens due to objects acquiring more and more mass. The more mass they acquire, the faster they will acquire new mass. So this is how our sun was formed, right? This is why things tend to have, and so the Pareto distribution, or Pareto, kind of Pareto's law, I guess you could say, is that things will get, there's an imbalance, right? Not every planet is going to be the same size in the solar system. You're going to have one massive center. That's because that was what got all of the mass first, and then started gathering all of the rest of the mass much faster than any other object could, right? And you could almost say that this is Pareto's law is for, remember, economics, but there is, you know, some definite there's definitely some commonalities between what we see going on in the world around us and these universal laws. And so that's why I wanted to tell you about it, just because I think it's super interesting that we see this happening all the time around us. Orbits, the speed of the object dictates the shape of its orbit, so you guys need to know that, the escape speed and how things are constantly falling in orbit. The inertia mixed with gravity is what forms orbits, so you guys need to understand that. And you guys need to know a little bit about the Kepler's law. So orbiting objects speed up close into the central object and slow down at a distance. So that was Kepler's second law, and then the third of Kepler's law is the farther away it is, the longer its orbit will take to complete one full rotation. So that's it for today. We will be doing some worksheets on the things you've learned so far to just kind of solidify this material and practice with it. But yeah, sorry, I know this one was probably pretty long, but there's a lot of really good information in here. But anyway, I'll see you guys later.